Okay, so I just wanted to go over the last example from lesson number 5 of reciprocal functions. And this is the one we didn't get to in class. And so if you were having difficulties with the homework and and you just weren't sure where to start with questions like this, where you're already given the reciprocal function. Okay, so this line here on the graph, which is y equals g of x, this is the reciprocal function of our original function that we actually need to plot here. And so we're given some information. So we're given the line of our reciprocal function, but then we're given the maximum point, which it has at -3 and 2. So this is at -3 and +2. And then we're also told that the y-intercept is at 1/5. So if we want to find out or we want to graph our original graph of y equals f of x, and then we also want to state the coordinates of the minimum point of y equals f of x. Okay, so first of all, let's look at what information we do have. If we're given the y-intercept of g of x, which is 1/5, then if we take this back to our original function, that means that the y-intercept of our original function was 5. So y-intercept was equal to 5. Because we know that to get to 1/5, the y-intercept of our reciprocal function, we just put this under 1. And so we're going to cross up here at 5. Now we're also told that we have a minimum point of this line here, which is -3 and 1/2. Oh, sorry, not 1/2, at +2. So at -3 and 2. And so if we were looking for the minimum point of our original function, remember that to get this, we put it under 1. But if we bring it back under 1, then what this is going to be is going to be 1/2. Okay, so our new minimum point for our original function is going to be at -3 and 1/2 down here. Okay, so our line is going to end up looking something like this. So that's what our original function looked like. Now, something else we can do is look at, well, I probably drew this a little too high, but we want to look at, first of all, our y-intercept, and that was at 5. We want to look at our minimum points. And in this case, we are looking at a maximum point at -3 and 2. And if we take the reciprocal of this, we're going to get -3 and 1/2, which would be our minimum point for our original function. And then we want to look at our invariant points. So our invariant points, and that's where y is equal to, in this case, only +1 because it doesn't go below the x-axis. So they would have similar points here and here, and then here and here. All right, so the point of symmetry, by symmetry, the point -6 and 5 is on the graph, but that doesn't really matter. So this is what our original graph would look like. And so then we want to determine the values of A, P, and Q if we write this in the form of y equals A times x minus p squared plus q. And remember, this is just the standard form of a quadratic function. So if we're looking to draw or write this in standard form, then let's think about what we have. We know what the vertex of our graph is, right? So that vertex is where we could put this original equation and split it symmetrically. So our vertex is right here at -3 and 1/2. Okay, so the vertex is equal to -3 and 1/2, which means P is -3 and Q is 1/2. So if we write it in this form, y equals A x minus P squared plus Q, then I can fill this in, and I'm going to have y is equal to A times x plus 3 squared plus 1/2. And what I'm looking for is my values of x and y, and I could just use my y-intercept for this, and my y-intercept for my graph, remember, is at y equals 5 and x equals 0. So I'm going to use the points 0 and 5 for my y-intercept, and I'm going to plug that into my graph. So 5 is equal to a times 0 plus 3 squared plus 1/2. 5 is equal to 3, this is 9a, 3 squared is 9, plus 1/2, it's going to give me 4.5a is equal to 9a, and a is equal to 2, or 1 over 2, sorry. And so my graph is going to look like this. Y is equal to 1/2 x plus 3 squared plus 1/2.